This webcast talks about how the kinematic equations that we learned when we studied the uniform acceleration model, how those kinematic equations connect to and relate to Newton's second law, which we have been learning with the unbalanced force model. So, the kinematic equations are equations which help us understand and analyze motion, and they involve several motion variables: the initial and final velocity, the acceleration, the elapsed time, and the displacement of an object. The Newton's second law is the law of motion which relates acceleration to the net force and the mass. And so Newton's second law involves those variables: mass, net force, and acceleration. The variable that ties both of these two types of equations together is acceleration. It is one of the variables used in Newton's second law, and it is also one of the variables used in the kinematic equations. Now that we have both types of equations available to us, we're able to answer some interesting types of problems. And basically the strategy will be that you will always first find the acceleration, either using a kinematic equation or using Newton's second law, depending on what kind of information is provided to you. And then you'll use that acceleration to answer the question. Let's look at a couple of examples. So in problem number 1 here, we have a race car that starts from rest and goes 40 meters in 3 seconds, being uniformly accelerated the entire time. We'd like to find the net force acting on the car. So the first thing that I'm going to do is make a list of the things that I know by reading the problem. So I know the mass. The mass is 710 kilograms. It says that it starts from rest. So that means that the initial velocity of the car was 0 meters per second, right? It travels 40 meters. That sounds like a displacement. In 3 seconds. That's the elapsed time. And it says that it is uniformly accelerated. That tells me I can use a kinematic equation, right? Because the kinematic equations only apply in situations where acceleration is constant. Okay, so what I want to find is the acceleration first, and then I want to find the net force, which is the sigma f. Okay, so I think that I don't have enough information to use Newton's second law at the beginning. I know the mass, but I don't yet know the acceleration. So I'm going to start with a kinematic equation, and I need an equation which involves these 4 variables: initial velocity, displacement, time, and acceleration. I think we're looking at the second equation, which says that displacement equals the initial velocity times time plus 1/2 the acceleration times time squared. This term right here, initial velocity times time, that equals 0 because the initial velocity was 0. That helps simplify this. I'm trying to solve for acceleration, and so I can say that acceleration equals 2 times the displacement divided by the time squared. So let's see what that is. 2, the displacement is 40 meters, the time is 3 seconds, and that gets squared. And so we get an acceleration of 8.889 meters per second squared. Now that I've found acceleration, I'm able, so the first strategy of this problem, first I had to find the acceleration. Then I'm going to use Newton's second law to find the net force. And so the net force equals the mass times the acceleration. Mass was given to me as 710 kilograms. I found an acceleration. And so when I multiply those together, the net force is 6,311.11 newtons. That is what the problem was looking for. Let's do another problem. So I'm just looking back at this one. Initially, I was given enough information to use a kinematic equation to find the acceleration. And then once I had the acceleration, I used Newton's second law to find the net force. In problem number 2, okay, so we have a car initially traveling at 25 meters per second. Its brakes apply a force of 5,000 newtons, and it stops. And the question is, what is the minimum distance required for the car to stop? I want to talk about this brakes applying a force. We're going to take this as the net force. So I'll do a little force diagram to try to make the situation a little more clear. There's the gravitational force on the car. That is 9,800 newtons, right? 1,000 kilograms times 9.8. The ground is supporting the car with a normal force. That is also 9,800 newtons. I know that because the car is not moving vertically, and so it is, those two forces are balancing. I'm kind of seeing the car moving to the right. And so if it's moving to the right, the brakes are going to apply a force to the left. So I'm just going to call it a braking force on the car by the brakes, or maybe an applied force on the car by the brakes. So that is my net force in this situation. Let's make a list of the things that I know. So I know the mass is 1,000 kilograms. I know that the initial velocity is 25 meters per second. I know the net force is 5,000 newtons. I know that it's going to stop, and so the final velocity is 0. And I would like to find the displacement of the car as it stops. Okay. So in this kind of situation, I do not have enough information about the motion of the car to use a kinematic equation yet. I only know the initial and final velocities. But I do have enough information to use Newton's second law. So here the first step is going to be to use Newton's second law to find the acceleration. So I know that acceleration equals the net force divided by the mass. Oh, and you know, I'm sorry, I'm just noticing, I really should have written that the net force is negative 5,000 newtons, because that force does point to the left, given that I am seeing the car moving in the positive direction. So that's going to be negative 5,000 newtons divided by the 1,000 kilogram mass. So it's negative 5 meters per second squared. Okay, now that I know the acceleration, I can use the kinematic equation to find the distance. And I need a kinematic equation that involves initial and final velocity, acceleration, and displacement. And that's going to be the third equation, vf squared equals vi squared plus 2 times the acceleration times the displacement. I'm solving for displacement, and so that would be the final velocity squared minus the initial velocity squared divided by 2 times the acceleration. If you notice, my two negative signs here are canceling, and so the displacement is going to be 25 squared divided by 2 divided by 5. And that's 62.5 meters. That's the answer that we're looking for. So these two examples show the range of problems that we'll do that involve the connection between Newton's second law and the kinematic equations. In both of these problems, the first task is to find the acceleration. Now, the way that you do that might be different. Sometimes you'll have enough information to use Newton's second law to find acceleration. Sometimes you'll have enough information to use a kinematic equation to do that. But the first step is always to find the acceleration, and then you'll use the other set of equations to find the answer to the question.